Honors Pre-Calculus students, welcome to today's 8.2 notes. Today we're looking at operations with matrices. Primarily, we're going to be talking about multiplication. We will have a little scalar multiplication, but then we're going to multiply matrix by matrix, which requires a little more thinking. But first, we're actually going to start with just the basic ideas. And so let's take a look at this. This says to find x and y. Well, what I know is for these two matrices to be equal, the same places have to have the same values. So 2x plus 6 has to equal 12. We can subtract and divide, and very quickly we have found x. I'm going to use a similar process to find y, so it's y equals y squared. Remember, you cannot divide by y in this situation or bad things happen. Instead, we're going to move both terms to the same side and we will factor. And by the way, you could move everything to the right instead of the left. It doesn't really matter. Either way, you get two possible values for y. It's either 0 or 1, where x has to be 3. Pretty straightforward in my opinion. Alright, so the next topic we're going to look at is linear multiplication. Also, we'll do a little addition in here as well. When we talk about linear multiplication, it's a fairly straightforward process. Like on this number 2, it says 2a. That means basically we just take the number 2 and multiply it by matrix A. And the way we do that is we think of it almost as distribution, where we just simply multiply each element of our matrix by 2. Pretty straightforward process there. Alright, let's take a look at the next one. A plus 3b. Now I'm going to go ahead and rewrite A. There's 3, negative 4, 5, and 2. And I'm going to add 3 times b. So I'm going to go ahead and multiply b by 3 and write it here. Negative 3, 6, 0, and negative 9. And then again, we'll just add the same parts. So 3 plus negative 3 gives us 0, negative 4 plus 6 is 2, 5 plus 0, and 2 plus negative 9. Alright, the last one on this page, B plus C. Now here's something to think about. Matrix B is a 2 by 2 matrix. Matrix C is a 2 by 3. You can't do that, folks. They have to have the same dimension in order to add or subtract. So we say it's not defined. You can't add B and C since they don't have the same dimension. Alright, before we get into our matrix multiplication, I want to talk to you about the idea that's going on here. So let's say we had two matrices. I'm going to call the first one A, B, C, and D. We'll call this matrix A. And then matrix B, I'm going to also keep it fairly generic. I'm going to say it's E, F, G, and H. Now the idea behind matrix multiplication is that you're going to take the first row of the first matrix and multiply it by the first column of the second, and it would look like this: A times E plus B times G. Once you've done that, you stick with the first row, but this time we'll multiply by the second column, and that we put in as row 1, column 2, so it's AF plus BH. Okay, continuing on. Once we've exhausted every column in the second matrix, we'll go on to the second row in the first matrix, so CD, and we multiply by first E and G, so we'll have CE plus DG. And then finally, we do C and D times F and H, so it would look like C times F plus D times H. I know this is a bit tedious, but it's really not that horrible of a process. Here's the thing you'll have to pick up and keep in mind. When we're talking about matrix multiplication, notice in this case we had 2 by 2 matrices. And the key to this whole thing is that these middle terms have to be the same. If you wrote it out this way, the number of columns in the first matrix has to equal the number of rows in the second. So a 2 by 2 multiplied by a 2 by 2 would give us, and it's what's left, would give us a 2 by 2. So if we thought of it in other words, let's say you had a 2 by 3 matrix and you wanted to multiply by a 3 by 5. This would be possible because 3 and 3 are the same, and you'd end up with a 2 by 5 matrix. Okay, now we'll see some more examples of this as we move ahead. So let's do a little multiplication. First, we'll do A times B. I'm going to go ahead and rewrite these. I think that's a wise thing to do when they're not laid out for you. And we'll go through the steps that I showed you just a moment ago. We're going to do row 1 times column 1. So that's 3 times negative 1 plus negative 4 times 0. That's our first entry. Then we go 3 times 2. This is our second column in the first row, plus negative 4 times negative 3. And once we've finished with that first row, then we go to the next row. So we'd have 5 times negative 1 plus 2 times 0. So 5 times negative 1, 2 times 0. And then 5 times 2 plus 2 times negative 3. We can, at this point, we can just simplify all these numbers. We'll get negative 3 plus 0, so that's negative 3. 6 plus 12 is 18. We'd have negative 5 plus 0, and then 10 minus 6. And there's our matrix. All right, let's take a look at number 6. Notice that the first one said A times B. This one says B times A. So all we're doing is switching the order. Now, one thing we know is that when we multiply numbers or binomials or just about anything else that we've multiplied, the commutative property tells us it doesn't matter which order you multiply those in. So if the commutative property works in this case, we should get the same result we're about to find out. So here we go, negative 1 times 3, that's negative 3, plus 2 times 5 would be 10. There's my first entry. Then we do negative 1 times negative 4 and 2 times 2. So we're done with our first row. Let's go to the second row. 0 times 3 plus negative 3 times 5. And then finally 0 times negative 4 plus negative 3 times 2. And then our final step is to simplify these. 7, 8, negative 15, and negative 6. Pretty quickly you're going to realize that is not the same as what we saw on number 5. So that tells us right there we have a good case. We have some evidence that the commutative property does not apply to matrices. Okay, and then last one we're going to look at on this slide is C times A. Now, let's think about this for just a moment. C is 2 by 3. A is 2 by 2. Folks, the key numbers here are this and this, 3 and 2. They're not the same, so we would just put not possible or not defined would be a reasonable way to explain that, but you can't do C times A. Interestingly enough, we could do A times C. If you switch those around, it would work and it would give us a 2 by 3 matrix. But C times A, not possible. All right, let's continue on with this concept. So here we go, B times C. So I'm going to go ahead again and write down the matrix. That was some quick writing. Okay, one thing to keep in mind, you can see the dimensions on these two matrices are different, and some of you might be looking at this and saying, wait, is this even possible? Well, B is 2 by 2, C is 2 by 3. You can see the 2 and the 2 that are in the middle here are the same. So what I know is we're going to be left with a 2 by 3. Now we don't really have to do all this work. It kind of works out naturally as you do the problem, but let's take a look at it and see what happens anyway. Okay, so we're going to have negative 1 times 1 plus 2 times 3. Then we'll have negative 1 times 7 plus 2 times negative 4. And then we haven't run into this yet where we have a third column, but we have one here, negative 1 times 3 plus 2 times 0. All right, let's take a look. We've gone through every column in the second matrix, so let's go to row 2. 0 times negative 1 plus negative 3 times 3. 0 times 7 plus negative 3 times negative 4. And then 0 times 3 plus negative 3 times 0. And we'll go ahead and write these out. Once we simplify our numbers here, we have matrix B times C. And as you can see, we've gotten a 2 by 3 matrix, which is exactly what we predicted at the beginning. All right, let's look at number 9, A squared. This isn't a horribly complicated problem, but sometimes people get a little sloppy with it and make unnecessary mistakes. When we talk about A squared, what we're saying is A times A. Folks, if you go in and try to square the individual entries, it will be wrong. There's really not a nicer way to say that other than it'll be wrong every time, at least close to every time. Okay, so again, write it out and multiply row times column just like we've been doing. 3 times 3 is 9. Negative 4 plus 5. 3 times negative 4 is negative 12, and then negative 4 times 2, negative 8. 5 times 3 is 15 plus 2 times 5. 5 times negative 4 plus 2 times 2. I know I'm doing this kind of quickly. I'm following the same pattern over and over. It's really one of those things with just some practice. You start to get really fast with it, and it's still a little tedious at times, but the difficulty level is not that high. Just learn the pattern. And there's your result. And you'll notice this has really no connection to if you tried to square the individual terms and had like 9, 16, 25, and 4. It's not the same. Okay, so don't try doing that. It will be wrong. There is one exception to that that you could run into with the identity matrix. There may be a random one out there that I'm unaware of, but it's highly unlikely that you're going to end up with a good answer if you do this process wrong. Okay, last one we're looking at today, C squared. Now, immediately when I see that problem, my eyes are drawn to this. This is not a square matrix. It's a 2 by 3. And if I try to take a 2 by 3 and multiply by another 2 by 3, I have a problem. The number of columns does not match the number of rows. So I stop right here. We're done. Not possible. So again, this would bring up the idea of like if you're going to square a matrix, what kind of dimensions do you have to have on that matrix? All right, folks, I hope that this lesson has worked for you. We'll get plenty of practice on this multiplication. I think if you learn the patterns, you'll find it to be a very reasonable concept, sometimes tedious, but not horribly complex. Have a great day.